Where did we leave off? I can't even remember.
We were past that.
Okay. Thank you. Okay. So I was told that we left off here. I can't remember. So that's what happens when you're old. You guys have any questions about anything we talked about so far?
I have questions about those bonds. That's in chapter 5.
Oh, you're going to learn about bonds. Trust me. Okay, so uh, so we talked a little bit about sodium, right? You guys understand that sodium is like an explosive metal, and then chlorine's a poisonous gas. But if you combine the two, then you end up with salt, right? Which we use every day.
So why did you put chlorine in the pool then?
Hmm?
Like, the chlorine kills the bacteria in the pool. Is that why you put it in the pool?
Yes. Well, it's not. I mean, it's more for algae than bacteria, but it will do both. Yeah. So it's deadly.
Is it potassium? Is it potassium? Potassium chloride that you can drop in water, so just.
Yeah, potassium is explosive too. So I'll show you guys a demonstration of some people throwing sodium metal into water. That looks photoshopped. Oh, we gotta watch a commercial first. So that's a piece of sodium metal reacting in water. I used to do the same demo, but the risk assessment people told me I couldn't do it anymore because it was a fire hazard. Sorry, what? I don't know. Uh, I mean, you guys can look later on if you want. I'll show you.
So, really quick while you're looking for that,
Mhm.
if we put salt in water though, it doesn't do anything. Is
That's
it
right.
because it becomes it, does it become, what were we talking about today, the more ionic or something, the ionic?
When it bonds with the other chemical, it becomes its own.
All right, so so while you're watching this demonstration,
They really just do that.
yeah, they're the chemicals are different once they've interacted, and we're going to talk about how the bonds are formed, the ionic bonds are formed. This will blow up in a second. Uh, but water actually can surround them too, so that it forms a hydration shield. And we'll talk about that in chapter 3 as well. All right, don't try that at home. So the point is that when you have two elements that interact, they change their chemical and physical properties, right? Completely different ones. And just like we talked about in lab, shape is really important too. So the shape of the molecules are different. Sodium and chlorine together have a different shape as well.
Can you separate them once they're in solid form by adding water?
Yeah, so water forms what we call a hydration shell around sodium and chlorine, and that's how things dissolve. Right? In fact, anything with a charge can dissolve. But we're getting ahead of ourselves, so let's talk about how it gets a charge first, and then we'll talk about in chapter 3 how water can make things seemingly disappear by dissolving them. So, life requires about 25 chemical elements. Like I told you, there that purple line on the periodic table. Most of the stuff above that is things that we're gonna talk about because those are the molecules, the elements that we're interested in that make up most of life and are required for life. The things below that, some of those are trace elements, but for the most part, that's more for a chemistry class. Okay. So the four elements that were mostly 96% living things are carbon, oxygen, hydrogen, and nitrogen. Right? And those are up at the top of the periodic table on the right. The remaining 4% are phosphorus. Phosphorus is found in DNA. Sulfur is found in proteins. Calcium in your bones, and potassium is required for animals to produce energy, like the energy that's found in your muscles. We'll talk about the sodium potassium pump in chapter 6 and 7. Any questions about that? All right, so this is a biology class, not a chemistry class, and that we're going to focus on only specific aspects, just enough chemistry for you guys to learn biology. So one thing that's important, and we're going to come back to this later, is that you are mostly oxygen by mass. 65% of your body consists of oxygen. Okay? And we're going to talk about that a little later on when we talk about the affinity of things for electrons. So I might ask you on a test, what are we mostly made out of based on mass? And you guys would answer oxygen. Good. All right, so when we look at elements, these elements are the smallest form. We can't break them down anymore, and they still retain their chemical and physical properties. So once we get smaller than an element, we get into what we call subatomic particles. Do you guys know what those are? What the subatomic particles of elements are? Right, so we have protons, neutrons, and electrons. And they're smaller particles, but we don't really care about that because that's more of a physics class or a quantum mechanics class. So each of these have a unique mass, they have a unique charge, and they have unique properties. Protons are positively charged elements. They have a +1 charge. Right? They have an atomic mass of 1.007. Neutrons are no charge. So basically what we do is we truncate this off because we're not building any nuclear weapons or anything like that, so we don't really need to know. We can round it off, right? We don't need to know that it's 0.007. And then electrons are negatively charged, and and this is Dalton's, by the way. And their mass is 0.010,000 of a Dalton. But again, that's too small. So for us, for all intents and purposes for biology, we can just say that their weight is negligible. So any questions about protons, neutrons, and electrons? All right, so the most important thing is for this class is that you guys are able to predict what the subatomic particles are that make up each of the elements. All right, so the periodic table helps you do that. If you look at the table, you'll see that hydrogen has a number, a red number above that. Right, what number is that? One. Right? So helium is over there. What number is above that? And sodium, you guys remember what that is? That's Na, so that's 11. So that number, that red number, tells you how many protons each one of these elements contain. It's called the atomic number. And it's different for every element. No element has the same number. You see that? Alright, so the number underneath it is the atomic mass number, the one in black, and that tells you its mass in Daltons. The numbers are long and weird because it's an average of all the isotopes, the different forms of that element that's found on Earth. Okay, so you can sort of round them, and I'll show you an example. So let's look at hydrogen. It's I don't think I have a marker that writes. You think they'd get pissed if I wrote on Sharpie on it? Okay, so hydrogen's atomic number is 1. So if we want to break it down into protons, neutrons, and electrons, we know that that has 1 proton. If it had 2 protons, it wouldn't be hydrogen anymore. What would it be? Helium. So we can't change the number of protons. We know that that has a mass of approximately 1, right? And so every time we have a proton, to make it electrically neutral, this is a positive charge, what charge do we need to negate the positive charge out? A negative, right? So what gives us a negative charge? So in an electrically neutral atom, if we have 1 proton, we have to have 1 electron. What's the mass of that electron? So it's okay, yeah, but let's just say it's 0, right? Because we're biologists, we're not nuclear chemists, we're physicists. So this total mass is 1, right? And what's the mass number of hydrogen? Yeah, it's roughly 1. It's 1.008 or something. So if I know that I can't have any neutrons in here, because if I did, that number wouldn't be 1 anymore. If I added a neutron, what would it be? Well, yeah, neutron's mass is 1, so 1 plus 1 would be 2. So we know there's no neutrons. So hydrogen is composed of 1 proton and 1 electron. Does that make sense? All right, let's try a harder one. Let's try one that you guys are familiar with, like sodium, for example. So how many protons, electrons, and neutrons are found in sodium? Okay, so sodium, its number, the number up on top is 11. So we know that it has 11 protons. That's what makes it sodium. If it had 10, it wouldn't be sodium anymore. Right? It would be neon. So if we have 11 protons, how many electrons?
11.
All right, so we know that this mass is 11 total, but what does the mass tell you underneath that sodium is? All right, so if your grade is 89.8988, what would you think I should do with it? All right, so what should we do with sodium if it's 22.898? Alright, so we'll say it's 23. So we can take the mass number and subtract it from the atomic number, and that gives us the number of neutrons that we would need to make it weigh 23, right? So we can say that it has 12 neutrons, and let's check our work. 11 plus 12 is 23. Alright, so you guys get it? You think you can do that? If I threw out an element at you on a test, that you tell me how many protons, neutrons, and electrons are in it? Yeah, so yeah, I'm not going to cover the periodic table. You can, in fact, you guys on this side of the room that can't see the periodic table that well, you can bring your own periodic table to the exams and just print it out. In chemistry, I had a professor that made me memorize the whole periodic table, but I'm not that cruel, so I'm not going to make you guys do that. If you're not sure, right, if you haven't had chemistry before or whatever, it's okay. You're just going to have to practice a little, right, at this. So that's why I suggested you guys get that book, because it has, practice problems for this, and you can check your work. But I'm not going to spend a whole lot of time on showing you how to figure out the subatomic particles for each one of the elements. It's relatively easy, right? Let's do one more. Let's do carbon. So what's carbon's number? So many protons? 6 protons. How many electrons? 6. What's its mass? 12 minus 6 is, so how many neutrons? There you go. Got it? Alright. Alright, so let me back up a little bit. I know a lot of you guys have already had chemistry, and this is probably very boring, but it's important that you understand. Did I just lock up the computer? It's important that you guys understand how chemical reactions work, and to be able to predict what chemical reactions are going to occur, because that's going to be able, it's going to enable you to be able to synthesize compounds, right, or know what the drugs are that you're prescribing patients, how they work and how they're synthesized. So for those that don't know much about chemistry, the protons and neutrons, they exist in what we call the nucleus of an atom. So you can kind of think of it as like the Earth, right? And you guys know the Earth has satellites spinning around it that give you your direct TV or your XM satellite radio or whatever. So the nucleus is protons and neutrons, and spinning around them are the electrons. Okay? So kind of like the satellites. And that's what's shown here. So
In that cloud is that those little things that you know on the right? The exact the little what
Cytoplasm?
is that what they're called?
no, that's different. That's a cell. This is an atom. Anyway, so it's depicted as a cloud because the electrons spin at close to the speed of light. So it's going so fast that it appears to be, one cloud around it. But if you stopped it, if you froze the electrons, you would see that they look like this. So and this is helium, so it has how many protons? 2, and so the artist drew 2 plus charges. That's correct. How many neutrons? Well, what's its mass? 4, so 4 minus 2 is, so it has 2 neutrons, and those are shown in black, so that's correct. And then, because it's electrically neutral, if it has 2 plus charges in the nucleus, it needs 2 minus charges, so that makes 2 electrons, right? So this is a typical helium atom. and these electrons spin around it. I don't know what's going on with this slide, but I'll skip it. All right, so I think everybody gets it. The atomic number is the number above on the periodic table. That tells you how many protons are in each element. It's unique for every element. In a neutral atom, the number of protons equals the number of electrons. Exactly. So we can figure out all of that from the mass number and the atomic number. So on a test, I might, make up an element and have you tell me how many protons, neutrons, and electrons are in it. Or I might give you one that's real. You never know with me. All right, so the mass numbers, like I said, are unique because they're averages of all the different isotopes. And by the way, this word iso you're going to see again because there's a term called isomer. Iso means same. Right? So tope is type. So these isotopes are the same types of elements. They just vary in their mass number. So a good example of this is carbon. So what's carbon's normal mass number? That's the atomic number. Mass number is 12. So we say that this is carbon 12. But there's also a carbon 13 and a carbon 14. So you guys probably heard of carbon 14 maybe. They use it to date fossils and things like that because it's radioactive. Well, do these have the same number of protons? Yeah, because if it didn't, it wouldn't be carbon anymore. The number of protons determines the element. So, right, so the only thing that we can vary, each one of these carbons, let's look at this one, has 6 protons, right? And so that particular one has 6 electrons to make it neutral. And then how many neutrons would it have? 6, right? So this is a typical carbon 12. Carbon 13, we can't vary the number of protons, right? If we added electrons, it wouldn't be electrically neutral, and not only that, adding electrons doesn't really add mass. So the only thing that we could do to get this to be 13 mass is to add a neutron. All right? And so, without getting into too much of quantum mechanics, if you have 2 positive magnets next to each other, what do they want to do? They want to repel, right? So you've got these positive and neutral charges in the nucleus of an atom. What does it want to do? It's a bunch of positives. They're not negative, right? They're neutral. You have a bunch of positives in the nucleus. What does it want to do? It wants to come apart. So the number of neutrons help stabilize those positive charges so they don't see each other. But when you start adding in neutrons, it makes the shape of that change, and so then the nucleus becomes unstable. Does that make sense? When the nucleus becomes unstable, things become radioactive. Radiation is basically the emission of particles or waves out of an element. Does that make sense? So when we start piling in neutrons into this thing, it starts to become unstable. And when we get 2 extra neutrons in there, which is what happens in carbon 14, this becomes radioactive.
And that's what they mean, right? When they say carbon dating.
Right. So, yeah, so you can use carbon 14 to date how old living things are. And there's a specific reason why. It's pretty straightforward. So everybody understand that these are isotopes of each other. And there's other ones too, like if you're looking at some things you can't see, like I can't see molecules of DNA, but if I put a radiation on them, just like if you went to your doctor and got an x-ray, you can't walk around and see other people's broken limbs, can you? because then they wouldn't need an X-ray machine. They just hire you, right? You walk around and go, okay, yeah, that's a broken tibia. Well, same thing with DNA, right? You can't walk around and see DNA, but if you put radioactive material in DNA, then it will, you expose it to X-ray film just like you went to the doctor, and you can see where it's at, right? So DNA contains phosphorus. So like phosphorus, its normal stable state is what? What's its mass? Should be 31, right?
Yeah, it's 30.9.
Yeah, close enough to 31. So there's a phosphorus 32 and there's a phosphorus 33. So this one is stable. These two are radioactive. And there's a sulfur. What's sulfur's normal number? This one is radioactive. So these are isotopes, right? They're the same element, but they have different masses. Does that make sense? Because they have different number of neutrons. So I might ask you what's an isotope on a test, and you guys should know that. All right. So let's go back to carbon, right? So you guys built molecules. I think both labs built the molecules, right? So I can use the fact that you guys built them. So you know that you built glucose molecules, right? And those have carbons in them. So elements occur as a mixture, right? So those glucose molecules that you built, you link them together in long chains, right? And we said long chains of glucoses are, you remember? Yeah, what kind of sugar?
No.
That's two. Two's maltose, but what's more than two? No, that's a fat. It is polysat, but there's a name. It's on your nutritional label. Carbohydrates. That's it. Carbohydrates. So where do you get carbohydrates from? Bag of Doritos? Safe to say? So let's say you go home and you're eating Doritos or whatever with carbs in it. But I don't care, potatoes, you can make it up. So if you shrunk yourself down, those are all made out of, I mean, you guys know that there are carbons in there, right? Lots and lots of carbons. Trillions of carbons in a bag of Doritos. Well, of all of those, 98.89% of them are carbon-12, right? About 1.11% are carbon-13. But a very small number, trillions, I'm not sure what it is, but billions, trillions, whatever it is, very small amount are carbon-14, right? So when you're eating these things, your body is assimilating them, right? You're what you eat. So your body is taking in this carbon. So here's a question. Can your body tell the difference between carbon 12, 13, and 14?
Well, you said it was spelling it inside.
Well, in molecules, right? We're talking about atoms now. The answer is no. So as you're eating, you're becoming 0.000000001% carbon-14, right? Well, no, I mean, it doesn't matter how much you eat because it's still just a percentage, right? It's a percentage of what you are. Because everything on the earth is that percent of carbon-14. So you have to eat proteins. You guys, when you built the protein molecules, right? What did those have in them? Do they have carbons? When you guys built the fat molecules, what did they have in them? So all the stuff we use for energy to live that we turn into ATP is carbon. So there's a percentage of carbon. As you eat, right, you become this percent of carbon. In fact, when you were an embryo, your mom ate for you, right? And so even then, you were a certain percentage of carbon-14. What happens when you die? Do you get, what happens to the percentage of carbon-14 then?
Goes into their lungs.
So, okay, so what happens is that carbon, radioactive carbon-14, decays. It doesn't like to be in this state, so it will convert one of its, so this is carbon, that's carbon-14, right? 8 plus 6. It will convert one of these neutrons into a proton and an electron. And it can do that. It's quantum mechanics. I don't care that you know that. So this neutron becomes 7. This becomes 7. And this becomes 7. So what is that? Is it stable?
Yeah.
What's the mass?
14. So yeah.
So it becomes radioactive carbon. The radioactive carbon becomes stable nitrogen, right? And that happens at a specific given amount of time that's relatively constant. It's 5,700 years, give or take 50 years, where that's what we call its half-life. So if I had a brick of carbon-14, I set it on this table, and I walked away, and 5,700 years later, I walked up here, and I tested it, half of that would be nitrogen, and the other half would be carbon-14, right? Then, if I walked away for another 5,700 years and I came back, half of the carbon-14 that was left would become nitrogen. So how much of the brick would be nitrogen now? No? It's a half of a half, right? So it's 3/4 nitrogen and 1/4 carbon-14. And then if I left another 5,700 years and I came back, it would be an 1/8 and a 1/16 and a 32nd, and so on and so forth. So once a living thing dies, it starts, the carbon-14 that you've assimilated starts going away, becoming nitrogen after your death, because you're not taking any more in. So you can use that to estimate the amount of time it's been since that living thing died. It doesn't work on rocks because they don't take in carbon-14, right?
So what if
But it works on
all-
living things.
What if it's all nitrogen? So what do you say to that?
It never would be. It would be so small that you might not be able to measure it, but it would never
So how
be
old would you
100%
say it would
nitrogen.
be then?
Huh?
How old would you say it would be if you can't measure how small it is?
I'm not sure exactly what the cutoff is because I don't study carbon-14, but it's like instruments get more and more sensitive as time goes on. So, I would imagine they can probably measure. I know that atomic force microscopes can detect single atoms, so I bet they can measure carbon-14 down to a few atoms. So you're probably looking at, millions of years you could use to date it. And then they use something else, right? They will use something else that's radioactive that its half-life is longer. But everybody understand half-life? And we measure proteins in half-life too, right? So like if you guys went outside and it was cold, then you would produce proteins that made you self-warm up. What do we do to help us warm up if we go outside and it's cold? You shiver, right? So if those proteins didn't have a half-life, if they were completely stable, what would happen if you got back inside and you warmed up? Well, you keep shivering, right? That would be lame. So you need your proteins to be unstable so that they break down so you don't sit there and shiver for the next 3 hours or whatever. So proteins are unstable because of that. Do you have a question? Oh yeah, this is going to be on the test, this formula. I'm just kidding. This is just a natural log of the ratio of the amount of carbon-14 as the factors of nitrogen, so original and then carbon-14. This is a constant, and then this is the half-life of the radioactive material that you're looking at. So, I mean, I'm just showing you that you can use this to date how old, fossils are. And we use radiation all the time. So, you know, you guys did the word problem about Debbie's thyroid, right? That uses radiation too. So it's important that you understand about radiation and half-life. You don't want to give a patient something that has a half-life of 5,700 years. It would never get out of their system.
Yeah.
The things that we use in humans, like this, has a half-life measured in like a couple days. So, all right. So everybody understand about half-life and isotopes. So I might put on the test P32, P33, and say, what are those?
Isotopes of phosphorus.
Isotopes of phosphorus. Everybody get it? All right. So we want to talk about electrons because you guys know that all atoms have a nucleus, and you know that if we have chlorine and sodium, that they're going to interact and produce sodium chloride. So what's going on here that causes them to interact to make sodium chloride? And so let's just pretend like we've shrunk ourselves down, and this is the nucleus. Let's make sure everybody can see this. So this is the actual size of the chlorine nucleus, and this is the actual size of the sodium nucleus, right? And you know that there are electrons spinning around it, right? So if this is the actual size of the nucleus, where would the electrons be? Here? Here?
Way bigger.
Here?
Like big football field.
Here?
Like big football field.
So if this was going in that direction, it would be somewhere around the 202 area. That's how far away the electrons are from the nucleus. So you're right, they're really far. So when these two things come together to react, what's the first thing that they encounter? The electrons. So the nuclei, we don't care about. All we want to know, because I told you, we want to predict the reactions, right? So the things that are reacting, the things that are interacting are the electrons. And that's why we need to figure out what the electrons look like, what the clouds look like, where are the electrons located. And to do that, we have to make predictions based on what we know about the subatomic particles in each one of the elements. All right, so I'll give you an example. I told the guys in lab a little bit about this, but I'll just repeat it because I don't have everyone for lab. Electrons are kind of like books in a bookshelf. So you have a nucleus, and you have an orbital that the electrons are in. So we number the orbital, first orbital, and second orbital, and third orbital, and so on and so forth. Now, let's say electrons are all the same size, right? And let's say you have a bookshelf. So you put so many books in the bookshelf, and then once that's full, you have to go to the next shelf, right? There's no like half shelf. So you can't have an electron halfway here, because if you did, the book would fall off the shelf. And it's the same way with atoms. So either the electrons are here, or here, or here, but they have to be on a shelf. They can't be on a half shelf. They can't be on a quarter shelf. There's no such thing as that. And each orbital only holds so many electrons. So this orbital right here holds a maximum of 2 electrons, just like if you had a bookshelf that would only hold 2 books. Once that's full, if you got 3 or 4 books, what do you got to do? You got to use 2 shells, right? You fill the first one, you go to the next one. So let's predict where the electrons are. We don't care about these inside shells, right? We want to know what's on the outside because that's what's going to interact with our other atom. That makes sense? So let's figure out what the electron configuration of sodium looks like. You guys help me out. So this one holds 2, this one holds 8, and the third one also holds 8. And in fact, I could lie to you and say the fourth one holds 8 and so on and so forth, but it really holds 32, and I don't really care because we're not really going to deal with anything that's going to have that many anyway. So just if you take chemistry, remember that 4 orbitals can have more than 8, but for our class, 8 works good. So we don't need to know any more than that. Everybody cool with that? All right, so don't go to your chemistry teacher and say, that Obermiller, he's dumb, he doesn't know anything about chemistry.
So there would only be one on the very outside.
All right, so let's go through it, right? So first of all, sodium, what's its mass number? Mass number.
20.
And what's its atomic number?
11.
So we know from this data that it has 11 protons and 12 neutrons, right? So that's what's in the nucleus. And then we also know from this data that it has 11 electrons, right? And this is really what we care about. So electrons travel in pairs. So in the first orbital of sodium, we have 2 electrons. They're paired. Everybody okay with that? So in the second one, we fill our bookshelf up like this. So we have 1 here, 1 here, 1 here, and 1 here. And then they start pairing. Okay. So then what's next? We got 2 plus 8 is 10. No, we have 1 more. So this is an unpaired electron on the outside. Everybody got that? Okay, so what about chlorine? What does it look like?
Got 17 protons, 17 electrons.
Okay, that's good. I'll accept that. So what's the electron configuration look like? First orbital has how many? 2. Second has
8.
I'm going to box these off so you can see that these are paired electrons. All right, and so we have 10, and then how many do I have on the outside then? 7. So 1, 2, 3, 4. I'll just skip that. 5, 6, 7. Okay, so it's got 1 unpaired electron in its outer shell. Do they agree with that? And then that one has one unpaired electron in its outer shell. This has 1 total electron in its outer shell. That has 7 total electrons in its outer shell. We got it? All right. So that's the electron configuration. And basically, this is what your book shows you. So for neon, it has 10, so there's 1, 2 in the first, and then 8 in the second. This, I don't care that you know this. This is more advanced chemistry. There's different orbitals, 2s and d's and e's and f's, and I don't even care that you know that. It's not important. It doesn't matter to us.
So when you're making sodium chloride, those single electrons bond together? They pair together?
No, they don't. They don't, because this is unique. All right, give me a second and I'll get there. Okay.
Okay, this might not be important. Valence reality places I'm curious. So why don't they? They're all negative charges, so they're all equally distanced around the shell. Why are they paired? Pushing against each other.
So it has to do with quantum mechanics, and they have to have opposing spins. So if one's spinning clockwise, the other one spins counterclockwise, and and they they're they're intertangled, right? So they're building quantum computers, so you can have one electron that spins one direction, and you could have something in France. If you change the spin, the other one would change. So it's kind of like binary, where it can tell, and you can send a signal faster than the speed of light doing that. It's really weird. It's called entanglement theory. You should read it if you want something to just make your head explode. Yeah, they've made a movie. It's called What the F Do We Know? And it's really, I mean, it's trippy. Like, you think you know stuff, and then you're like, whoa, that's weird. But, I love that crap, right? My wife thinks that I'm crazy. I'm like that. I told my other class, I'm like that Cox commercial, where the lady's like, I will stream Netflix and all that stuff, and the guys in there is like, don't bother me because I'm in a parallel universe. That's how I am, right? I'm like, so anyway, what happens is that and this is just the diagram here, but there's a rule. It's called the octet rule, but that's kind of a misnomer because not all of the outer shells have 8 electrons. But most of these elements wander around and they're completely unhappy. Like, they're unsatisfied. They're not fulfilled because they don't have their outer shell filled. That's their goal in life, right? Yours might be to, meet somebody and settle down and have a white picket fence and a car and, kids. Theirs is, I want my outer shell filled. And so sodium, does it have its outer shell full? But it wants to be full, right? It's sad like this. So what does it have to do to fill its outer shell?
It has to gain 7 electrons.
So it can gain 7 electrons. Or there's another alternative, right?
Can it lose an electron?
Right. Or it could lose 1 electron, right? If we got rid of that electron, its outer shell would only be 2, but it would be full, and that would make it happy. It wouldn't be sad. This is sad sodium. We want sodium to be happy. So what do you think's easier? Losing 1 electron or gaining 7? Yeah, so you'd be right. Okay? It's much easier. And then we have chlorine over here, which is not satisfied either, right? Because its outer shell is not full. And we can make it full. What do we have to do? So it can gain 1 electron. I'm just going to use the E minus as an electron. Or it could lose. What do you think is easier? Well, it just so happens that sodium comes along, right, and says, "Hey, chlorine, what's going on? I got this extra electron, and I don't want it. Can you take it off my hands? It's like that bad kid that you have. Can I just take it?" And chlorine's like, "You know what, sodium? It's what a coincidence, because I've been looking for one of those electrons for a long time, and I would love to have your electron." So sodium gives chlorine its electron. Now that whole shell collapses because we can't have a partial shell. And so now they both have a full outer shell, right? So they're both happy.
But they're both not stable.
Well, they're stable, but there's a problem, which is this one has how many protons
11,
and how many electrons?
10.
So it gave its electron away. So it only has 10. So if you have 11 plus charges and 10 minus charges, what's your charge?
1.
You have a 1 positive charge.
So
So yeah, so it's positively charged. And chlorine now has gained this electron. And In reality, sodium doesn't give the electron. Chlorine is kind of a bully, so it comes up and says, "Sodium, give me your electron," and sodium's like, "Okay, here." So chlorine's got the electron, and there's another problem here because how many protons does this have? 17, because we can't change that. It wouldn't be chlorine anymore. And how many electrons?
8.
So, okay, so now chlorine's like, okay, thanks, sodium, I'll be on my way. And sodium's like, yeah, me too. But what happens when you have a positive and a negative charge next to each other? So now they're stuck with each other forever. Right? And so that's a chemical bond. They can't escape from one another because they've done this electron transfer. Sodium's given chlorine its electrons. So the transfer of electrons produces a chemical bond called an ionic bond. Right? So chemical bonds are transferring or sharing electrons. That's all it is. There's ionic bonds, which I just taught you guys, but there's also a kind of bond called a covalent bond. So a covalent bond is basically when two atoms come up to each other and they're of equal strength. So I told you chlorine is a big bully, right? We measure the strength of an atom to be able to keep its electrons and take electrons from others as what we call electronegativity. And so things over here on the left, they want to get rid of their electrons, right? So they have a weak electronegativity because their goal is to dump their electrons on somebody else. Because they have just a few in the outer shell. These, their outer shell's mostly full, right? So they have a strong electronegativity. They're not going to give up their 7 electrons because they just need to get 1. So these atoms are stronger at taking electrons from others as opposed to these. And chemists have gone through and assigned actual number values that are just from 0 to 4 of the electronegativities of everything. So the ones over here, like helium, its outer shell is full, right? So it doesn't interact with anyone. It's, it's like, atoms come up to it and go, hey, helium. And it's like, mind your business, I'm busy, Neon, all of these, they have outer shell is full, so they're not interested in any other atoms. They don't react. We call those inert, right? They're also called noble gases because they don't interact. They don't participate in any chemical reactions. They just are. The strongest electronegative molecule is fluorine, right? Which is right there. Fluorine is so good at grabbing and keeping electrons that once an electron is on fluorine, it's almost impossible to get it back off. So that's not very good for us because we want to be able to reverse reactions like the sugar. Oxygen is the second most electronegative element. The reason we breathe oxygen is because it has an affinity for electrons. Because we want to flow electrons. Because flowing electrons produces electricity, and that's what makes ATP. I'll show you that in chapter 9. That's why we breathe air. To move electrons from carbon But we can use those numbers to predict how things are going to interact. So, I'm going to give you an example of the electronegativity units. Okay? So, I'll give you guys these on an exam. I don't expect you to memorize them, but these help you predict what kind of bonds are going to be formed. So I'm going to go back. This is pretty simple. Two hydrogens walk into a bar, right? So you have two hydrogens. They're going to come up to each other, right? One hydrogen has how many electrons in the outer shell? And how many does it want? Another hydrogen comes up to that one and says, I have one electron and I want your electron, right? The other hydrogen says, no way. You go ahead and take it because I'm using it. I want your electron. So they get in a big fight, right? Over electrons. But they're the same size. They're the same strength. So what's the ultimate outcome of this? They quit. They're like, all right, forget it. Let's just share. And electrons move so fast that they don't know the difference, right? So when two hydrogens, I lost my mic. When two hydrogens come up next to each other, we have one electron in the outer shell. They share that pair of electrons. So in essence, they spin around so fast that this one at any given point thinks it has two because it's moving so fast, right? And this one thinks it has two as well. So they're happy, but there really is only one pair. There's really only two. So this bond, the sharing bond, is called a covalent bond. Alright? And that's different than someone taking your electron, like chlorine did to poor sodium. Valence? So valence is the number of unpaired electrons in the outer shell of an atom. So for example, if we looked at oxygen, right? Oxygen has how many electrons in its outer shell? On its outer shell? 6. So it wants 8, so it has 2 unpaired electrons. If you went and did it like I did, you would see that it would have 2 unpaired electrons. That means its valence is 2, and that means it will form 2 bonds. Does that make sense? Well, let's not get into that, right? That's chemistry. Let's just stick with the, yeah. Let's not talk about that. I don't want to get into that.
That's the multi-bond thing.
Right. So for example, carbon, right? Remember when you guys played with the balls and sticks? The black ball had how many holes? 4, because carbon's valence is 4. It has 4 unpaired electrons. So you can look at carbon. How many electrons in its outer shell? 4. So it has, if I went around there and went 1, 2, 3, 4, you would say there's 4 unpaired electrons. So its valence is 4. You know, you could look at fluorine or hydrogen, right? What's its valence? 1. So, all right. So, and there's another term. I don't want to freak you out, but you might see it, and it's in your book, and it's called valence electrons, which is different. So, oxygen's valence is 2, which means it has 2 unpaired electrons, but its valence electrons are 6 because it has 6 electrons in the outer shell. So valence and the term valence electrons are 2 different things. Unless you're carbon, they're the same. Does that make sense?
So the valence electrons are just the outer shell.
Number of electrons in the outer shell. Valence are the number of unpaired electrons in the outer shell. And that predicts, valence is more important because really what we're predicting is what bonds are going to be formed. How many and what kind. Does that make sense? Because that's the most important part hard in predicting chemical reactions and, more importantly, what chemical reactions are going to occur inside living systems.
So for purposes of illustration, when we had those bonds, or the chemicals that we formed when we had two extra moles sitting on
In nitrogen, yeah. So nitrogen's unique because it can form transient bonds with extra molecules, and we'll talk a little bit about that. It's unstable, so it causes it to have a positive or negative charge, but it can take on like extra hydrogens and stuff like that.
So that would be its valence.
Nitrogen's a little hokey. Like, it's typical valence. If you look at nitrogen, how many electrons in its outer shell? Last I checked, it had 5. So remember we talked about you could gain 3, right, or lose 5. Well, sometimes nitrogen gets confused and it goes the other way, so it can make 5 bonds instead of 3. That's why there's 5 holes in that thing. But most of the time it goes the normal way, which would be 3, right, and that's more stable. So when they made the nitrogens, they made them in case you were going to build something with the screwy nitrogen, not the normal
That's what we
one.
were talking about for purposes of this class, it only has 3.
Yeah, exactly. Because its valence is 3, so you would predict that it would form 3 bonds. You know, and this is science, so there's always some sort of weird, screwy organism like, you know, platypus that lays eggs. It's a mammal, but it lays eggs. Who would have thought, you know? But there's always some exception. But that's what it means. All right, so you can form more than one bond, right? You could share 2 pairs of electrons, like in oxygen. So oxygen's valence is 2, right? So it has 2 unpaired electrons. But if you have 2 oxygens that come together, they can share those 2 pairs. And so if you count, like, so this is sharing 1 pair and that's sharing another. But if you count these, how many in the outer shell of this one? I'll tell you it's 8, all right? And then this one, 8. So it thinks, because it's sharing 2 pairs of electrons, it thinks that there's 8 electrons around each one. So it's sharing 2, and that's the double bonds that you guys built in lab. And those are unique. Remember, they can't rotate where single bonds can. All right, so just keep that in mind. This is important.
You know if I get a double bond, how is it?
This one?
Yeah.
So it's sharing 2 pairs of electrons. So there's 6 here, 6. Let's say that this is one of the unpairs from this one. 1, 2, 3, 4, 5, 6, and this is the other one. 1, 2, 3, 4, 5, 6. So it's sharing these 2 pairs of electrons. And each a shared pair of electrons, 2 electrons that are shared, is 1 single bond. You can have triple bonds, right? And how many electrons would it be sharing then? 3 pairs, right? 6 total.
No, as electrons rotating the same way they rotate around the hydrogen. Right?
So
Once they bond, like once you bond two sets of electrons, how are they rotating? They're not, right? Because they're gonna rotate.
okay, so electrons are weird. They can disappear and reappear. They can become full energy and full matter at any time, and they can move. You can have an electron that's flowing around this atom and then end up around an atom in Mars and come back here. So technically, there's no way to predict that. That's called Schrodinger's cat is the thing. So you can't predict where an electron is unless you look at it, and by looking at it, you've changed it irreversibly in some way where your prediction of where it was at can never be truly accurate. So don't worry about how the electrons flow around it, because you'll never know. This is just made up, right? I just drew that on there just as an example. But it's good enough, right, for this class. Okay, so water forms this way, right? Oxygen and hydrogen, but they're not the same. They have different strengths. So how do you know if they're going to share electrons? And in some cases, even if they end up sharing, they may not share equally, right? It's like I bought this boat with a friend of mine who lives near Lake Pleasant, which is like way out in Glendale. And I thought, oh yeah, I'll go to the lake and whatever. Who do you think uses the boat more often than me? Him, right? So we're not sharing equally. We're supposed to, but we don't. So, in some instances you don't share equally. Does that make sense? And that's the same way in the atomic world. So oxygen's a lot stronger, I told you guys, than hydrogen is. So who do you think gets the electrons more often? So I'm going to draw my fake drawing, it's figure eights. But it works. Alright, so we have oxygen. And we know how many unpaired electrons in its outer shell?
3.
Well, okay, let me draw. 1, 2, 3, 4, 5, 6. So how many unpaired electrons?
2.
Alright, so this is oxygen. Hydrogen comes up to it. How many electrons?
1.
So these share. Does that make sense? They're spinning around, right? They're sharing. Here's another hydrogen. It has 1, so it's going to share these. So everybody thinks they're happy, right? They all think that they have an outer shell filled. And that's because the electrons. And then this one became all energy and went to Mars and then came back. But, they don't know that because it's going really fast.
So how much water would that make?
This is just one water molecule.
Yeah.
Okay, but oxygen is stronger at keeping electrons. So what do you think the electron spends more time around, oxygen or hydrogen? Yeah, in fact, it spends a lot, 3 or 4 times more time around oxygen. Sometimes it spends so much time around oxygen, it forgets about this hydrogen. And then it just falls off. And it's sad. It doesn't evaporate. Like, there's a law of the universe that says you can't create or destroy matter. You can only change it into energy and back. So it's the law of thermodynamics. We're going to cover that too in chapter 8. But for right now, trust me, they don't share equally. So oxygen gets a sort of a charge on it, right? A partial charge. And so we call that a sigma charge, because a whole charge means that you've lost or gained a whole electron, right? So we have, 10 minutes? What time is it? 5 minutes? Yeah, it's blinking at me, so I can't turn it on. I called them and asked them to come and fix it. They probably were like, that dude's crazy. Like, they didn't sit in here for an hour and wait for it to shut off, It's like, taking your car to the shop and they're like, what? I can't repeat the issue, sure. Anyway, so a full charge would be a +1, right? And this isn't happening. It's only a partial charge. So we say it's a sigma charge, and then we give it a negative. It's not a full charge, it's just a partial charge. And then if the electrons stay around here more often, what do you think the charges are on the hydrogens? Yeah, they're partial positive charges. No, it doesn't. Because the electrons can spend a lot of time around here. what holds them together is the sharing of the electrons. It has nothing to do with the charges. These are relatively weak charges, but they're still significant. Anyway, so because this is shared unequally, we say that it's polar, right? Because when you think of a pole, like the North Pole has a charge. And so if we're saying something's polar, we're saying it's not shared equally, so it sets up these partial charges. Right? And then the other one would be, if we had two hydrogens sharing, they share equally, so that wouldn't make a charge, right? So we say that that bond is, what do you think? Well, they're all covalent if they're shared. It's not bipolar. It's non-polar, right? Because there's no partial charge. All right, so there's three kinds of bonds that we talked about, right? One is ionic, and that's when the electrons fully transfer to another element. Then they set up a full charge, full +1 for sodium, full -1 for chlorine, and they stick. That's an ionic bond. Sharing are covalent bonds. So that's a covalent bond, that's a covalent bond, right? But there's two subclasses of covalent bonds. One is you share equally, and then you're a nonpolar bond. Does that make sense? Or you share unequally, and you're a polar bond. So we have ionic and covalent, and then the covalents are polar and nonpolar.
So if oxygen is a polar bond, does that?
So it's not oxygen, it's oxygen bound to hydrogen. Two oxygens bound to each other would be nonpolar,
Right.
because they share equally.
With it down to two hydrogen,
Right.
it's not sharing equally, so it's a polar bond.
That's a polar bond, yeah. That's a polar bond.
So is the H and H also polar?
No, because they share equally.
I'm talking about the way they share with oxygen.
No, there's no bond between these two. The only bond, so if you were to build the atom, like everybody built the water, right?
Yeah.
So when you built it, you had an oxygen, and then you attached two hydrogens to that oxygen. You never attach the hydrogens to each other, because there's no bond between the hydrogens, right? The bond is with oxygen, and that's important. So you're looking at individual bonds. You can have a molecule that one of those bonds within a complex molecule is nonpolar and the other one is polar. That's quite feasible. But here, when we're talking about these simple molecules, this is polar and this is nonpolar.
So like we're talking about the lab, you want to break down something, you add water to it. You want to let it grow, keep water out.
Right.
So how do you break down H2O?
So that's different, right? We're talking about macromolecules with those reactions. Water, you can't break it unless you interfere with the sharing of the electrons. Does that make sense? So you would have to, oxygen can do it by keeping the electrons around it. This would come off. This happens all the time, right? When you go home and you drink a glass of water, a certain number of those water atoms are going to do this, right? So this keeps the electron, right? So this one has an extra electron, so what's its charge now? It's no longer a partial charge, it has an extra electron, it's negative, right? So this is what we call hydroxyl, which is one of the functional groups you guys learned. And this is a hydrogen ion. Now, it won't last long because this is going to realize I don't have all the electrons that I want in my outer shell, and it's going to be like, I got to find this lost hydrogen. And the same thing is going to happen with this. So they'll go back, right? But this occurs at 10 to the minus 14 molar of hydrogen ions. And this has to do with pH. Because every time one of these is made, one of those is made, right? So that means that if this is a constant, then this has to equal this, right? Because if one of those is made, that's made. So that means this is 10 to the minus 7, and this is 10 to the minus 7. Because together they're 10 to the 14th. So the pH of this, of pure water is, remember its power of hydrogen? It comes from that number right there.
So that's why you can't break it down.
Right.
All this different factors.
Yeah, I mean you could, but it won't last long, it's transient. Alright, so everybody make sure that you guys get ionic, covalent. If you don't, you should practice this stuff because we're gonna leave this behind and we're gonna start talking about how we balance equations, how reactions occur, and stuff like that. And that's going to lead us into this sort of stuff. So if you don't know this, you're not going to get this. Does that make sense? So over the weekend, I would brush up on basic Chapter 2 chemistry. If you're lost, I strongly suggest you try to find that Chemistry for Biology Students book, or at least try some practice problems by asking Google, because it has a lot of questions too and answers. No, we're about halfway through Chapter 2 right now. Oh, now it works.